Rock Deformation, Video 2, Folding. In the last video you might remember about the relationship between stress and strain and how it links to rock deformation. Stress is the force that we apply to a rock, whether it be vertical or horizontal from whatever angle, whereas strain is the resultant change in shape or volume. So we can look on this diagram now. Let us just increase the stress we're applying to a piece of rock. You'll notice that it changes its shape and volume. It might be compressed, it might be sheared in one direction, but there is a change in shape or volume. But the first part of the change of shape is what we call elastic deformation, which is where if we don't apply the pressure anymore or the pressure comes off, it will return to its original position. This is called the elastic limit. However, beyond this point, if we keep applying stress, then the rock will permanently deform. The first stage of that deformation is ductile deformation, which is commonly called folding. And on the left there you'll see a picture of some folds in some rocks in Morocco. Beyond this point, as we saw in the last video, the rock can't bend anymore, so it will snap, which we call the yield or fracture point, and we know that as faulting. There's some examples of some faulting in Norway. There are some basic features of a fold that have to be learned. Firstly, the idea of the wavelength. Now the wavelength is the distance between two adjacent points. I've just chosen it as the crest here, these 2 points, and that distance there will be regarded as the wavelength. The amplitude is half the wave height. So we take a central point from the wave, as you can see there, we measure down to halfway between the bed, and that is amplitude of the fold. Now remember, very much like faulting, all folds are caused by compressional forces, as we see from this diagram here. Before we move on to look at some other features of folding, just a reminder about two different laws that apply to this section. Firstly, the law of original horizontality, which says that all sedimentary rocks were laid down in order and flat. The law of superposition says that rocks at the base are older than rocks at the top. So rock A, rock B, rock C, rock D. Rock D will be the youngest, rock A will be the oldest. Other features of folds that we need to know as well. You can see in this cross section how the rocks that were originally laid down flat have since been tilted, have since been folded. The direction of dip, look at the north arrow on the block diagram, therefore the direction of dip as shown by the arrow is in an easterly direction. The dip angle, and you can see the angle it cuts with the horizontal, is 60 degrees. So we could say the dip angle is 60 degrees towards the east. And finally, don't forget the strike, which is at right angles to the direction of dip, and that would be a north-south strike. Antiforms and synforms are common questions at AS level, both from diagram form and from map form as well. We commonly refer to them in AS as anticlines and synclines. There is a subtle difference between them. An antiform is a type of anticline shape, but we can't ascertain if it's been overturned or not. The syncline is the part of the downturn fold, whereas the anticline is the upward part of the fold. The axial plane is the point of symmetry of the fold, and the axial plane trace is the point where the axial plane cuts the surface, sometimes called the APT. We can also describe parts of a fold by the angle of hinge. There are 4 different types you can see in the diagrams here. A gentle angle, an open angle which is regarded as 90 degrees or more, a tight angle which is regarded as 20 degrees or less, and an odd shape there, an isoclinal, which is where we have beds that are parallel to each other. We can also describe the shape of the axial plane. In this diagram, the axial plane, shown by the orange 3D box, is upright. You can see the axial plane trace marked as the green line. However, not all axial planes are upright, are vertical. Some of them can be, as you see in this example, might be horizontal. This is called a recumbent fold. Here's some examples to show you these different points. This is an upright attitude of the axial plane, whereas on this diagram you can see quite severe folding. There's the axial planes, so we can say that they are horizontal attitude. True and apparent dip. Sometimes difficult to show in examinations. They might just refer to something as true dip. But you can see from this house what we mean. A true dip is the steepest part, in this example, of the roof. It's the point that goes straight down. But in our 3D world of geology, sometimes rocks are cut at a certain angle, and the angle of dip therefore would look less, but we call that the apparent dip. Remember from our fieldwork, to work out the true dip of a rock, put some water on it, and the water will find the steepest angle. Now, there's our law of original horizontality. There's our beds of rock that are laid down. Oldest to youngest. This is that same group of rocks folded into a syncline. But don't forget, weathering and erosion wear down the rock, and it might be worn down to this shape. Now, it's important from your examinations that you remember what happens in this type of block diagram. A was the oldest rock, B was the second oldest rock, C was the next oldest, but D was the youngest. So on this diagram you can see the youngest rock on the syncline is in the centre, and as you go further out you get to the older rocks. Let's look at that if we put a map above the block diagram. Hopefully you can see it linking there. There's the youngest beds in the middle on the map above. There's the next oldest beds there, and there's the older beds themselves. So look at the pattern it makes on the map above the block diagram. There's the axial plane, and the axial plane trace will be where it cuts on the surface. The dip arrows on the map would show this direction of dip. They'll be dipping in towards the axial plane because it is a syncline. Again, looking at the past paper question, there's line A to B. There it is on the diagram, roughly the same sort of colour scheme. Look at the key, you can see the youngest on the older beds on the syncline. Again, don't forget the symbols that we use on geological maps to show the syncline and the anticline. And we can see that's the syncline diagram straight down the middle of that. An anticline is the opposite. There's again the oldest beds and the youngest beds at C. We're going to fold it up and then we're going to wear it down. But this time you can see it's the reverse from the syncline. The oldest beds are at the core, are at the centre of the anticline, and the younger beds are towards the edges. Okay, a basic question to follow on what we learned so far. How do we know if this is an anticline or a syncline? Pause the video if you want to try and work it out for yourself. First of all, have a look at the key. The oldest beds are shown in white. The youngest beds are shown by the lines. Now, if you look, the oldest beds are at the centre of the shape, and therefore that would make it an anticline. Now, also other information we can see from there, once I put on the dip arrows onto the map, you can see that we were right, it was an anticline. One further question from this past paper question was the arrows to the north of the map weren't given any values. So can we work out if the folding is symmetrical or asymmetrical? Folds are classed as symmetrical if their limbs are the same length. It's nothing to do about the way they dip. So you can see from these two diagrams that both of them are symmetrical because they have the limbs on either side of the axial plane are the same length. However, on these diagrams, they're regarded as asymmetrical because they are different length limbs. Here's one example from the French Alps. I've superimposed the lines there to show you the length of limbs. You can see the unequal length of limbs in this folding, and therefore these folds are regarded as asymmetrical. One issue you're always given on map work is about having different outcrop widths. Now if you notice from the top cross section, we have 4 beds of different dips. A, B, C and D. Now look at the cross section, they are the same width. However, the angle they cut with the surface means that rock D has a far wider outcrop than at A. Looking just at the map to start with, you might think that D was a much wider bed, but you can see it's the angle it cuts with the surface makes a difference. D is a much more gently dipping bed. This also works with a fold. 2 different parts of a fold there, and underneath you can see the surface outcrop. That one is dipping at 80 degrees in that direction. That one is dipping at 40 degrees. You can see it's part of the syncline. But you can see to the right, this area has a much wider outcrop. Going back to our original diagram, do we know if there's an asymmetrical or a symmetrical fault? We don't know what these arrows show. Would they be more or less than 30 degrees? First of all, we can't tell if it is a symmetrical or asymmetrical because we don't know the length of limbs. We can't ascertain that from this diagram. However, what we can say is that to the north, L1 is a much steeper bed than L2. That's because the outcrop, as you can see here, is much thinner than down here. So L1's bed would be much steeper than L2.